So in this video I want to talk about the second moment of area, otherwise known as the moment of inertia. And if you're looking to find the moment of inertia for composite sections, I'm actually not going to talk about that in this video. I will talk about that when I cover the parallel axis theorem. But before that, I just want to kind of go into a little bit of theory and do a quick derivation just to give you a better sense of what second moment of area is. So a quick definition it basically indicates how area is distributed with respect to a specified axis. And just like the first moment of area, you have to have, we're assuming constant density throughout the section and constant thickness. So if you have a coordinate system and you have a section here, call the distance from the y-axis to the centroid to be x and this distance to be y. So the second moment of area is given as a times, well, we need to define the axis that it's with respect to. So Ix, with respect to the x-axis, it would be the y distance squared. And the second moment of area with respect to the y-axis would be the area times the x distance squared. And this squared tells you that it's the second moment of area. It's kind of self-explanatory in the name. For when we're finding centroids, we use the first moment of area. That's why the equation was x bar times the sum of a equals the sum of the little x bars times a. So that was just the distance to the first power. But for second moment of area, we square the distance to the axis. So the derivation that I want to do is pretty simple. So if we have a rectangular section, constant density, constant thickness, because it's constant thickness, we just consider the area. And I'll set my coordinate system right at the centroid. It's a little bit easier to do this derivation when it's at the centroid. So we know that if this is given as base times this is the height, we can look up the moment of inertia about the x and y axis, and this is given as 1/12 base times height cubed. The second moment of area with respect to the y-axis is 1/12 height times base cubed. So this is all tabulated information, but just to give you a better insight, I want to derive it. So we'll use a little bit of calculus here. So in order to find this Ix, I'm going to take a sample slice here. So I'll call this distance, that'd be delta y, and the distance from here to the x-axis is just y, because it's constant across through the whole piece. So again, if I want to find my delta Ix, which is the second moment of inertia just for this sample slice, that's going to be my area, or delta area, times y squared, just like this given equation here, a times y squared. So if we want to sum up all these pieces, we just have to put it into an integral. So my Ix is going to be the integral. Well, delta A can be further broken down to, let's see, delta y times the base. So delta y times b, which is constant, times y squared. So I plug that into my integral, the base times y squared times my delta y becomes dy in my integral. And my limits of integration is going to be from y equals this point to y equals this point. Well, since my origin is right at the center, this point at the bottom should be negative height over 2, and this should be the height divided by 2. So that should be my two limits of integration, negative h over 2 to h over 2. So my base, again, is constant, so I can pull that out. The integral of y squared, dy, is y cubed over 3, and that goes from negative h over 2 to h over 2. So let's plug that in. Some algebra. It would be h cubed over 8 times 3. That's 24. Minus, there's two minuses here. So it would be minus h cubed over 24. So of course these two minuses become pluses, and we'll have base times 2 times h cubed over 24, which reduces to base times height cubed over 12, which matches up to the tabulated information. So again, all it is just the area times the y distance squared for the second moment of area with respect to the x-axis. So similarly, we can find Iy. I mean, all we're doing is switching our distance. So again, here's my x-axis, here's my y. So this time I want to take my sample slice to be vertical. So this will be delta x. And the distance from the y-axis to this slice is x. So our delta Iy is going to be delta A times the x distance squared. Again, the delta area can be broken down into the area of this box again. It's going to be delta x, that's my base, times, well, what is this height? Well, that's just h, that's constant. It's h all the way across. So delta x times h times x squared. So I just put this into an integral to find Iy. So it would be h times x squared. My delta x becomes dx. And my limits of integration goes from x equals this point to x equals this point. And again, this is, if this is given as b, and my centroid's right in the middle at the midpoint of b, so this point should be negative b over 2, and this point should be b over 2. So my limits of integration goes from negative b over 2 to b over 2. So if I integrate this, this will be h x cubed over 3. Of course, the h is constant, so I can pull it out. Negative b over 2 to b over 2. And again, just like the last problem, it's pretty similar. If I plug this in, this should be b cubed over 24 plus b cubed over 24, which finally gives me hb cubed over 12. And yes, that's what we get in like the back of the book, or if you just look it up on Google. So again, in the next video, I'll talk about parallel axis theorem and how to find the second moment of area for a composite section, for instance, an I-beam. So if you have I-beam, how to find, the centroid is right here, how to find the second moment of inertia given the centroid.